Welcome everyone to the public lecture series, the first of the season. For those of you who arrived too early and I hadn't printed these up yet, there are many available at the entranceway on your way out. We have the full listing of our schedule for the next 6 months. So these events happen every month or so on Friday nights, starting at 8 p.m. or in the winter they start at 7 p.m. because the sun sets earlier and we can still observe quite early. And in case this is your first time, these are events sponsored by Caltech Astronomy as well as the National Science Foundation. And we have a lecturer from within our department, either a postdoctoral fellow like we have tonight, or a faculty member or a graduate student, talk about some area of research that they think is interesting, and hopefully you will as well. That lasts about 30 minutes, and then we have stargazing through telescopes directly behind the astronomy building on the adjacent fields, athletic fields, as well as we have a panel Q&A made up of members of the department to be able to answer whatever questions you might have about astronomy or physics or the universe or whatever. Hopefully we can address some of your questions. And you're free to come and go between the two, check out a view of Jupiter and then come back in here and ask a question about the birth of the universe. So this will go on until 10 o'clock and then we shut it down. So in addition, on the back side of our lecture schedule, we have a schedule for our Astronomy on Tap events, which are similar. They're less formal. They're at a bar. And we have 2 15-minute talks at a bar downtown in Old Town called Der Wolfskopf. These are once a month as well on Monday nights. Unfortunately, we can't get the bars on Friday nights because they're too busy. But on Monday nights, we have the opportunity to do these events. Again, like these events, they're free. The beer's not free, unfortunately, but we encourage you to come. So the full schedule of that is available. There's still seats around here and on the right side as well if you want to give it a shot. And I'll put out some more chairs on the side as well. It looks like the observing conditions are pretty good tonight, so we should have pretty decent views of Jupiter, Saturn, probably the Ring Nebula, probably M13, and maybe Albireo or Alcor and Mizar, which are a couple of binaries that are worth looking at. So there's lots of stuff to look at. A couple of rules with using the field. It's artificial turf, but it's this fancy artificial turf, and the athletic director gets really upset if any damage comes to it because it's only a couple months old. So you can't eat out there. You can't drink beverages other than water because if you spill on it, it's bad. You can't smoke, you can't bring out pets, you can't wear high heels on the lawn because it could puncture it. No canes, walkers, these sorts of things. This should be fine though. You should be okay with the wheels. So yeah, and there will be people reminding you of that at the entrance, but yeah, please don't do that. And in addition, try and keep cell phone use out there to a minimum, at least with your bright screens, because it's going to mess up your night vision, so you won't actually have as nice a view of the thing that you're trying to look at because your eyes are totally messed up by looking at these bright blue screens. So, okay, enough yammering from me. Our speaker tonight is Dr. Astrid Lamberts. She is a postdoctoral fellow here in the department in Caltech Astronomy. She did her PhD in Grenoble in France, and then did her first postdoc at University of Wisconsin at Milwaukee. And her research is related to the stuff that she's talking about tonight, but focuses mostly on binary star evolution and the full spectrum of different kind of stars and behavior that go into that study. So please welcome Dr. Astrid Lamberts.
Thank you, Cameron. Good evening, everyone. So tonight I'm going to be talking about what astronomers can learn or might soon be able to learn from the detection of gravitational wave events. So I'm not a member of LIGO. I'm not even a specialist of gravitational wave detections, but I'm really excited about what these detections are already telling us about the evolution of stars and the star formation in general. So far, there have been 4 detections that have been announced. And even the very first one has actually really challenged the way we look at massive stars. And so this talk is going to be about those detections, but also trying to give you an idea of what we hope is coming ahead of us. Because 5 years from now, we hope to have 100 detections. And so maybe this will, I hope, really challenge the way we think about the universe. So gravitational waves are ripples in space-time. What that means is, so space-time is a combination of the 3 dimensions of space and time. And what it really means is that it's our framework that we use to describe the location of anything that happens. We're sitting in a moment of space-time. We're in this room. It is 8:10 on July the 14th. And for our everyday life, space-time is a pretty easy concept. No, the size of this thing is never going to change. It's going to have the same speed if I'm measuring it in my car tonight, tomorrow, same. But space-time can actually be changed by very violent phenomena in the universe, by very dense objects. So this is a picture of 2 black holes or 2 neutron stars turning around each other. And so these are very dense objects, and what it means is that they will basically modify the structure of this fabric of space-time and create ripples. And so these are the gravitational waves. And if a gravitational wave comes through an object like this, its size is going to change a little bit. And so this is what was predicted by Einstein about 100 years ago in his theory of general relativity. And this is what has been detected for the first time directly with the LIGO detection about 2 years ago. So I'm going to show you a movie that was created by experts of simulations of general relativity. Some of the people are actually working in this building. And so what you see here are 2 black holes that are, the masses they have represent one of the systems that have actually been detected. And what you see is that initially, when these black holes are pretty far away from each other, these ripples are pretty small. And then as the black holes get closer and closer, the ripples get bigger, and they're also closer to each other. And then after the merger, that creates very big ripples, we don't have any ripples anymore. And this is the end of the gravitational wave emission. So this movie is pretty impressive, I think. When I look at this, it's like, wow, this is a huge thing. But you have to remember that actually those gravitational waves make really, really tiny changes in the measurement of certain distance. And this is why it took more than 1,000 scientists to work together for more than 30 years to actually build the detectors that would eventually detect them. So the LIGO is a combination of 2 detectors, one in Livingston in Louisiana, in the swamps, the other one in the desert in the state of Washington. They're as identical as possible. I will not go into the details of the detection, but it requires these very large antennas, sorry, you can see here, one arm here and one arm here, to be able to measure this really tiny effect. And so what they actually measured was this. So this is the signal that was measured by the 2 detectors over time. So in orange is one of the detectors, in blue is the other one. And so the first thing that you see in the very beginning is basically nothing. This is just cold noise. This is the thing that LIGO basically detects as we're speaking, presumably. And then as time goes by, you start seeing these ripples. And they get bigger and bigger and closer to each other until we reach the merger. And then it's over and we're back to detecting noise. And so the reason we're pretty sure that this is a real detection is because the 2 detectors, so the one in blue and the one in orange, saw or heard the same thing at the exact same time. And this means that it's not someone opening a fridge in Louisiana or, rush hour in Seattle or those things, because actually those are detected by the detectors, but it's only detected in one. And here we know both saw it. So it means it's a real detection. So the question is, okay, we see this. What does that actually mean? How do we use this to actually understand something in terms of astrophysics? Well, what we do is, and by we, I don't mean including me, experts make simulations of the mergers of black holes. And they basically make this very big library of all the possible mergers they can think about and then they try to find the one that looks like the detected one. And so this is the result of one of the simulations they created, and you see that it's very close to what they detected. And so it's basically by finding the close match that they can understand what happened here. And so what they find is, by combining this observation and the simulation of general relativity, they found that the mass of the most massive black hole, so what we call the primary, was about 36 times the mass of the sun, and the mass of the second one was about 29 times of the mass of the sun. So this is how we actually extract what I think is the most valuable information from the LIGO detections. This is my perspective, not everyone's perspective, but this is the information that astronomers think is very interesting. What are the masses we're looking at? So, okay, we have two black holes of 29 and 36 solar masses. What does that even mean? Well, let's start with what a black hole actually is. So we live on Earth, and on Earth, like everywhere else, there's gravity that pulls us towards the center of the Earth, which is why when we jump, we don't fall off the Earth. And this is because if you want to escape the gravity of the Earth, you need to go very fast. There's something that is called the escape velocity. It's basically the speed you need to have if you want to escape the gravity of a certain massive body. And so on Earth, if you go 10 kilometers per second, you come back. If you go 11 kilometers per second, you get out. And so this is about the speed that basically rockets have. This is why they have to go so fast. It's because they have to be able to escape the gravity of the Earth. Now let's imagine that we take the Earth and we make it 100 times smaller. We just push everything together and make it much denser. In this case, you need an escape velocity that is 10 times bigger, just because the Earth has become denser, so it's much harder to escape. Now, if we keep doing this and take the Earth and turn it into a marble, you really take the whole Earth and you push. Then, what you need to escape is 300,000 kilometers per second. So this may look like, just a number to you. But actually, this is just a little bit higher than the speed of light. And what it tells you is that if the Earth had the size of a marble, light would not be able to get out of it. So this means that if I'm an alien, I'm looking at the Earth, well, there's no light coming from it. So what that means is I can't see it. And that is an astronomer's definition of a black hole. It's not the only one, but that's how we actually have to deal with black holes in astronomy. It's something that doesn't emit light, and astronomy is based on looking at things. So this is something that actually has been bothering us for a very long time, is that we know these objects exist. We can somewhat know where they are because they can influence what's around them, but we've never been able to see them or actually really know what they are. This is where LIGO becomes a tremendous object, a really good tool. And LIGO is mostly going to tell us how many of these binaries we have, and as I said, what their masses are. So this is the list of the black holes, which masses we know. So the unit we use is the mass of the sun, because it's sort of a convenient unit for us. And here down are the black holes we knew before we had the LIGO detections. So these are all black holes that live in a binary with a regular star. And so the star and the black hole turn around each other, and it's basically by understanding what happens to the star that we can guess that there's a black hole with the mass that we can find here. And so what you see is that the lightest one we've been able to measure have about a mass of about 5 times the sun, and the most massive ones get to 10, 15-ish. Okay, so all these black holes, we were able to see the effects on the companion star, and so this is only possible very close to Earth, because they're hard to see. Now in blue here are the black holes detected by LIGO. So this is the very first detection, and you see the other ones here. And what you see is the very first detection has 29 and 36 solar masses. And so this is much bigger than what we expected from the the masses of the black holes we know of. And so really, the thing that is bothering us is, why are these masses so much bigger than the ones we know? When this came out, I just couldn't understand it. So all of these black holes are thought to be remnants of massive stars, so leftovers at the end of the life of the massive star. Just for your own knowledge, I want to tell you that there are other types of black holes called supermassive black holes. Those masses are about between 1 million and 1 billion. So if this is the mass scale, we would be high up in the atmosphere to actually see the mass. So these are very different black holes. They're in the center of galaxies. I will not really be talking about them, but you should know that they also emit gravitational waves, and it's also something astronomers are thinking about. But let's go back to stellar mass black holes. Really the question is, why do we have this difference? So that's what I'm going to be talking about. So the question is, how do we even make two black holes? How do we even get to the merger? So the first thing is to remember, okay, black holes come from massive stars. And typically you need a star that is at least 20 times as big as the sun. Because if your star is smaller, it will end up as a neutron star or a white dwarf, not as a black hole. So okay, we need two big stars. That's actually a problem, because massive stars are very rare stars. It's about one star out of 100,000 that will actually be this big. But we have a slight small gift from nature, is that actually most of massive stars, the way they actually form with a binary companion. So that actually helps us. Okay, we now have two massive stars. Thing is, these stars are so massive, they will actually create winds. They will basically continuously shed some of their material. And this will be a small effect in the beginning, but as the star evolves, it will get stronger and stronger. And so what it means is that your star is initially 20 times the mass of the sun, but maybe at the end of its life it's 14 or maybe 7. So you lose a lot of mass. So if you want to make a 30 solar mass black hole, that's going to be a problem. So this is an image from the Hubble Space Telescope of Eta Carinae, which is one of my favorite stars. I work on binaries, and I think this is a beauty. So in the very center, there are two massive stars that you can't see on this picture, but they both make very strong winds. And this is why you have these big bubbles. They're just blown from the winds of the stars. And this is also why you have all this hot gas around. And so in the middle, the winds of these two stars collide with each other, and this is why you have this very strong emission in the middle. So we use these binaries to understand how massive stars lose their mass. And winds are a problem. The other problem we have are supernovae. What happens is that, so the star is basically burning fuel in its core, and eventually it will run out of fuel. And when that happens, it explodes. And it explodes as a supernova. And when that happens, it's a very bright phenomenon. If it were to happen close by, we would actually be able to see the supernova with the naked eye during the day. It's been 400 years that it hasn't happened close by. Maybe we'll get lucky, I don't know. This is an image of a nearby galaxy taken at some random night. This is an image of the same night that was taken by undergrads who were doing some summer project in the UK and saw this star appear. This is really a supernova discovered by undergrads. It just popped out. And so what happens in the supernova is that the star is going to expel what is left of its envelope, and then inside in the core there will be a black hole. And so the envelope is going to make these beautiful remnants that we can study and find out about massive stars. So again, we have some mass loss here, so that's a problem. The other problem we have about the supernova is that, well, supernova explosions are actually kind of messy. And so there's a decent chance that it breaks your binary. And if you have no binary, you have no black hole merger. So the supernovae can be a problem. So let's assume that we did survive the supernovae phase. Now we have one black hole and one massive star. And this is what we call an X-ray binary. This is actually the phase where we can maybe measure the mass of the black hole, because it's going to be eating up some of the massive star. It's going to make an accretion disk, and then it will basically, the accretion on the black hole is going to make a jet, and that makes a lot of X-rays and radio emission, and we can actually study what's happening. And so the important thing is that some of the mass of this star is going to end up in the black hole. So that can actually change the masses that we measure. After this phase, what's going to happen is that the secondary star is going to become much older, and as stars get old, they get big. They inflate. And so a star that was initially like this is going to get big like this. And so what is going to happen then is called the common envelope phase. Don't bother with the name. It's a phase that we don't quite understand from theoretical perspective. It's something a lot of people are trying to work on. Some people call this the elephant in the room because it's a thing nobody really wants to work on because it's complicated. But the idea is that in the beginning of the common envelope phase, so one star is really big, the other one is the tiny dot here, and basically the star is going to be swallowed by the other one, sort of. And so this is a simulation of a common envelope phase in a slightly different setup, but that's okay. The idea is the same. And what it does, basically, the thing we care about is that initially the star was here, and now it's here. So it's going to bring the initially very wide binary very close to each other. And that is very important because if they never get close, they will never merge. So we hope that we will really be able to understand a lot of things about the common envelope just by knowing how many mergers we have. Because we know that at some point this needs to happen. We don't know how it works though. So then, well, we have one black hole and eventually a second supernova, where again, this can happen. But let's assume it doesn't. What we now have are two black holes. So all the description I've just given you, all this happens in 10 million years. And so 10 million years, for us it's a lot, but for astronomy it's really nothing. But now, the time from forming the two black holes to the merger is going to be 10 billion years, basically. So it is much, much longer. And for billions of years, the binary is just getting closer, so the ripples are getting bigger until we eventually merge. And so out of these billions of years, LIGO is going to see the last seconds at best. And there's all this happening before. And so what it means is that, because we need these billions of years, is that if we see a merger, it means the stars that actually made the black holes are actually very old stars and were born a very long time ago. So in a certain way, we can get information about how the universe was a very long time ago. And that's what I think is very interesting. So just to wrap up this part, this is a recipe for black holes. So you start with two really big stars. You need a few billion years. It is not easy. There's a lot of things that can go wrong. You take your stars, you let them reduce a little bit. That's the stellar wind part. You use a common envelope, whatever you have. You use a supernovae to turn them into black holes, and then you put them into your crock pot and you just wait. So that's a recipe. So because you have to wait this long, this is probably why these black holes and these black holes are different. Because the black holes here are the ones that still have the massive stars. So these are like 10 million years old, and these are a few billion years old. So they were formed in very different conditions, and this is probably why they're different, and it's why they're interesting. So, okay, these black holes formed, 5 billion years ago. What was the universe like 5 billion years ago? So I'm going to show you a movie of a cosmological simulation. So these simulations are basically trying to represent the whole evolution of the universe. And so the beginning that you see right now is the universe a very long time ago, and you will see a movie that basically shows as time goes by. So over here are stars. Well, initially there are no stars. Over there is the density of the gas, which, well, you can't really see, but it's basically very uniform. Not much is happening. Everything is very cold, and the bottom panel, which I will explain later, is called Metallicity. Don't worry about it. Just look at it. black so far. Is this working? Yes, it's running. So what you see is that mass, the gas becomes denser in certain points, and this is where actually stars can form. And as stars form, you see that pink stuff appears here. And so basically, oh, thanks. That's perfect. Oh, sorry about that. Well, just going to let this run again. If you remember from the last panel, at the very end, it's bright pink over here. So this means that stars are creating this thing called metals. And this is what it's going to be about. So now we're almost at the present day, and you see there's a lot of stars, and it was bright pink over here. So I used the word metal. Actually, that's a bit of a shortcut. In astronomy, everything that is not hydrogen or helium is called a metal. Don't ask. And so what it means is that in the beginning of the universe, there is only hydrogen and helium. That's what's made by the Big Bang. And so anything else is made by stars, and these are the things we call metal. And so this is a region of star formation. This is actually a zoom in the Orion Nebula that you have probably seen with a telescope. And so massive stars are forming here out of this hydrogen and helium. As they form, they burn. After they form, they will burn fuel in their core and create carbon, oxygen, things like that. And the winds will basically blow away these elements and bring them back to the gas cloud. Eventually, the star is going to explode as a supernova and also send away a lot of these elements and send them back to the cloud. What that means is that the stars that form after, basically the second generation, is going to form out of gas that will be different, that will be more rich. And so this cycle is going to go on until this becomes very, very rich. And so basically, if we look at what we call the chemical enrichment of the universe, we go from almost no metals to a lot of metals. And so these would be the time that this would be the time of formation of the black holes we can see in the Milky Way, ones we see with X-rays, and this is the formation time of the black holes we can see with LIGO, or at least some of them. And so in terms of metallicity, they're different. So why do I care? Well, let's think about a massive star. Massive stars are, well, very massive, which means that at the center, it is very dense. It gets very hot. And because it gets so hot, they make a lot of light. And so if we take a look at the atmosphere of these stars, and imagine a star that has few metals. So it's only made of hydrogen. So for me, hydrogen are red squares. Imagine all these are hydrogen atoms. What happens is that the light will basically hit hydrogen atoms, and this is how you create the wind. Basically, the light is pushing the atmosphere of the star and creating the wind. And if you don't have a lot of metals, the squares are rather tiny, so a lot of light will just go through and not really make a wind. So the wind is not that strong. But now, if you have a star with more metals, metals are bigger. Just really in terms of size, they're bigger. And so the chance of the light hitting one of these is much bigger. So what that means is that your wind is stronger. And what it means is that for a low metallicity star, you can end up with a big black hole because most of the mass will actually stay in the star. And so when the supernova explodes, a lot of the mass goes to the black hole and you make a big black hole. But if you have a high metallicity star, the star is going to basically shed most of its mass during its life. And you end up with a small black hole. This is one of the simple arguments to explain why certain black holes are more massive, just because they will probably form in a place with low metallicity. And that actually makes sense, because in the early universe, there were less metals. So this is probably what happened, at least for the very massive ones we've measured. So then I got curious. Okay, we're looking for low metallicity environments. We know that that happens in the early universe, but maybe there's a bit more. This is a picture of the Hubble Ultra Deep Field. This is basically the Hubble Space Telescope staring at a patch of the sky. And you see that there are blue galaxies, and blue means stars formed very recently. There are red galaxies, means that stars actually formed a long time ago. And there's tiny galaxies that you can't see. And so the question I'm asking myself is, which of these groups are probably going to make the big black holes I want? So I don't know the answer, but one way to look at it is to look at what we know around us. So let's think about our Milky Way. So the Milky Way is the galaxy we live in. And the Milky Way is actually a massive galaxy. It's about 100 billion stars. And the average metal content is about the one that we find in the sun. So the sun is a very average star in the Milky Way. And actually, in terms of global context, it's a pretty high metallicity. But that's on average. If you take a zoom, so this is real data from the Apogee survey taken down in New Mexico. Each point here is a star. And red means a lot of metals, blue means no metals. So it's taken from Earth, which is here, and you see that if you go to the center of the galaxy, you have a lot of metals. If you go out, you have less metals. But even then, there's a lot of variation. And so this means that even in our own galaxy, there are going to be low metallicity environments. Now, if we go to smaller galaxies, if you ever have the chance to go to the southern hemisphere, there are the Magellanic Clouds. There are two small satellites of our own galaxy. They're smaller, and their metallicity is about a quarter of the one we have here. So maybe that's a good place to start. We can even go to smaller galaxies. This only has 10 million stars, but they have typically, a metallicity of 10% of the sun. So they're going to be able to make really big black holes. The problem is they only have 10 million stars, so how many massive ones? Maybe a lot, maybe not, we don't know. And then there are very, very small galaxies with 500 stars that have really a metallicity that is smaller than 1% of what we have here. So those would be the ideal places to make really big black holes. But then they're so tiny that maybe they never made them. I honestly don't know which one of these models is going to work. I don't know, because there have been 4 detections so far. Oh, that's actually working quite well. And so we're really looking through the keyhole. There's 2 detectors, 4 detections. We don't quite know what we will end up. But soon, I hope we open the door and we can see the whole picture. So coming very soon, there will be the Virgo detector. It's in Europe. It's being tested right now, and it should be running actually by the end of the summer. There will be a 3rd detector. And then hopefully, 5, 6, 7 years from now, there will be a detector in Japan and in India. And so when that happens, well, these detectors will also be improved with respect to what we have now. So what it means is that we can have maybe 100 of detections. So we will actually know how many of these black holes the universe produces and how the stars evolve to get there. And what it also means that if you have 5 detectors, we can maybe know where the black holes came from and know which type of galaxy made them. And that, I think, is a very crucial part. But these are not the only gravitational waves that actually exist and that we can think about. There's something called pulsar timing arrays. There's a lot of people who work on that here at Caltech. And so pulsars are a special type of stars that rotate at a very fixed speed that we know well. And so the problem is that if you have a gravitational wave, that's basically shown here in green, going by a pulsar, it will slightly change that frequency. And so we can measure that on Earth. So that means that if you have a group of these pulsars and you time them very well, you can know if gravitational waves are passing by. And so this technique is very well suited to measure the supermassive black holes I mentioned in the very beginning. And so these are important because they tell us a lot about how galaxies have formed and have evolved over time. So I'm really looking forward to their first detections, which may be coming in the next few years. The other very interesting thing, I think, is LISA. So LISA is a European mission with a strong involvement from NASA. And a couple of weeks it was announced that it would fly in 2034. And it's a detector with 3 arms. It's basically LIGO in space. Each of these arms is about 100 times the distance from Earth to Moon. So it's huge. And so thanks to that, it will actually be able to detect the black holes before LIGO can detect them. So remember, for billions of years, they just get to spiraling and making these small gravitational waves. And this is actually one thing that LISA will be able to measure. And then it will also be able to tell where it is. And so it can tell the LIGO people, hey, in 2.5 years, you should be expecting something from there, because we know it's going to happen. And then you can use your telescope and get ready. It will also be able to detect some of the supermassive black holes I mentioned. And what I think is really exciting is that it will basically be able to see binaries from smaller stars as well. I haven't talked about it at all, but it should be able to basically detect every close binary in the galaxy. So anything that is turning around each other with a period of less than an hour, so in 1 hour the stars go around each other, LISA is going to see it. And so we're going to have a map of the galaxy that represents those things. And I think that is a beautiful thing. So I'm going to wrap up here. I'm not a gravitational wave astronomer, but I think it's really the new window on our universe. It will tell us so many things about how many stars are forming, how they evolve, in what type of galaxy they live. And it's going to be able to tell us a story about the universe over billions of years. I think that's an amazing story. Thank you. Yeah, questions? Anyone? Mm-hmm.
I know it provides different information if you have 2 detectors angled with the same angle or angled at 90 degrees apart, but would it provide any information that if they were at any other angles, say 45 degrees or 60 degrees?
So the orientation of the detector, so you've seen these 2 arms in the LIGO, the picture that I showed.
Right.
They matter. They can give us information. So we would have more information if the detectors were different, because then you can actually measure these angles. It was a choice in LIGO to have 2 exactly identical detectors, because then we can make sure that if we see something identical at both sides, it's a gravitational wave. There's no question asked. We understand what's happening. So it was a choice to have them exactly identical. The next detectors have a different orientation, so we will have some information as how the wave is coming in. So far, we don't really have that, but that was their choice. Yes, they're in the back.
Yes, you pointed out that in the galaxy, at the arms of the galaxy,
Mm-hmm.
metal content is less than towards the center. Any reasons why, any ideas as to why towards the edge of the galaxy you have less metal in the sun?
So the gentleman asked a question about the picture I showed about the metals in our Milky Way, and was asking why there are less metals at the edges, or where it seems to be. And so that's actually very true. And it is mostly because the stars that are outside are typically older stars. And so it means that they were formed out of less rich clouds, and this is why they are less metal rich. And typically the stars that are really nicely in the disk and close to the center of the galaxy are formed more recently and are more metal rich in a very general sense. So it is also possible that the stars that are further out, that are not even on this picture, come from tiny galaxies outside and were actually brought into our own galaxy. And then these stars would typically come from one of the small galaxies here. And because of that, they would also be less metal rich. So these are two reasons why on the outskirts it's typically less metal rich. Yes?
Could you explain LIGO? What is that? You talked about it.
So LIGO is the big machine that we built to make gravitational waves. So let's see if we can get there. So LIGO has, both of the detectors have two arms, so there's one here and the other one would go through the picture here. And inside you have lasers. And these lasers actually bounce back and forth in the arms. And what happens is that you have a mirror at each of the edges, and by measuring the time of arrival of the light between the mirrors, we can measure the distance the light has crossed. And because we know the speed of light, it never changes, we can very accurately measure this distance. And so if the distance changes because of the gravitational waves coming through, we will be able to know it because the light pattern has slightly changed.
So they're both linear?
Sorry?
So both linear?
They're both straight arms of 2 kilometers long. Yes. Yes?
How is Lisa going to be built and getting built in space? So enormous.
So I don't know the details. It's 3 detectors. As far as I understand, I think that means they have to make 2 separate launches because they can only fit 2 in one rocket. I think it's going to be all ready on Earth and that we're going to send them up, but I don't know the details. I'm not sure if anyone actually knows them. I mean, it's 20 years from now, so we know some of the technology, but some is still being discussed. Yeah?
How far back does Lisa look, like before the collision? Is it 2 years?
So the gentleman asked how far back Lisa will be able to see the black holes before we see them in LIGO. So that actually really depends on the mass of the black holes. If the black holes are rather small, like some of the detections, one of the detections was 7 and 14 solar masses, Lisa will not see that. But if it's about 30, then it's about 2.5 years. It depends on the masses. Yes?
Earlier question about the Metallicity,
Mm-hmm.
the outer stars are less metallic. You also said the supermassive black holes at the center of the galaxy, and they are typically less metallic. That's why we take more of their mass to become this massive black holes. So is there like a different distribution where it's like less metallic on the outside and also deep in the center of the galaxy also it's less metallic?
So the gentleman is asking what happens with the supermassive black holes at the center of galaxies and about their metallicity. So we use the word metallicity when we talk about gas and about stars. Black holes don't really have a metallicity. So when I was talking about the metallicity of stars, I was talking about the stars before they turn into black holes. So the black hole at the center of our galaxy doesn't really have something like a metallicity. And
the stars that light up.
so far actually we don't really know how we make these very massive black holes. There are different possibilities. One is that it's indeed stellar mass black holes that sort of get together at the very beginning of the universe and become big. But then probably most of the mass just comes from gas that's being fed into it. But the formation of these supermassive black holes is an active field of research, and I honestly don't know the answer to your question more than that.
One more question?
Aside from this project and the LIGO project, how will the Space Telescope itself, what else is understand about gravitational waves, ability for James Webb, or the Space Telescope?
Yes, so the gentleman is asking, aside of these 2 projects that I mentioned, what else can we use to understand gravitational waves, and especially the other astronomy project that we have, the big telescopes that actually use the light, the thing we've been using for so long. Absolutely. JWST, which is basically the new Hubble, will be able to look at the galaxies that I was showing and probably find these regions where the stars form and understand the metallicity in the early universe. Same thing with W first. There's also a lot of efforts, for example, at the higher energies, because, well, the problem is for when black holes merge, we don't really expect to see the black hole merger because they don't make light by definition. But if we have two neutron stars, we expect them to make light, and we are hoping to catch that. So there's a lot of development on trying to catch that at all wavelengths. So there's gamma ray telescopes meant to do that. There's X-rays. There's ground-based efforts in the visible light. There's going to be a lot. And a lot of the ground-based astronomy and space-based astronomy is going to be about making things working together. And I think that's the best thing, to have both the eyes and the ears.
Okay, let's thank Dr. Astrid Lamberts, please. Okay, thanks for sticking around for the expert panel Q&A. Our panel tonight consists of Chris Bohenik, who is, I've listed some of the different topics that people feel comfortable answering questions, but if you ask questions beyond these topics, we'll do our best. I mean, we do have studies beyond just our specific stuff. Mike Grudich, so Chris is prepared to answer questions regarding pulsars, fast radio bursts, and supernovae. Mike Grudich is prepared to answer questions about star formation, galaxies, and black holes. Masha Okunkova is prepared to answer questions regarding general relativity, gravitational waves, like we were hearing about tonight, and black holes. And then I'm Cameron, and I am happy to answer questions on a lot of stuff. But I listed the universe simulations in the space program. So, what questions do you guys have? Yes?
Do any of the like LISA and these other detectors that are coming out in the near future, do we feel they're going to be sensitive to detect any possible deviations from general relativity?
Oh, okay, this is a great question, because this, okay, so the question is, will any gravitational wave detectors be able to detect deviations from general relativity? And this is a nice question, because this has to do with my research. So my research, part of it deals with, so I do simulations of black holes, and part of my research is trying to do simulations in sort of beyond GR theories. So with LIGO, for example, and sort of I can mainly speak to LIGO, but you get sort of similar effects with LISA. With LIGO, there are a bunch of ways that people can detect deviations from general relativity. So when GW 150914, which was the first LIGO event, was announced, there was a companion paper which tried to look at, does this event show any evidence for deviations from general relativity? And for that particular event, they said that there was sort of no evidence, but as the instruments get more sensitive, hopefully we'll be able to sort of set, either detect a deviation or sort of set larger constraints. So if I can go into more detail, there are a bunch of different ways, and if you want to know, I can sort of list those, but I also don't want to take up everyone's time with this question. So, I mean, if you want to, and if everybody wants to hear. Sure. Sort of I talked about my research, so there's this effort to sort of produce these model waveforms. So with LIGO, as we saw at the beginning of the talk today, you really want these waveforms from simulations, and you try to match them to the data. And so ideally you would have sort of other theories of gravity where you would produce these waveforms and try to match them to the data. However, we're sort of limited by this because we don't yet have waveforms in other theories. So what you have to do is kind of do other sort of things with the data. So some people make these kind of comparisons between the first part of the waveform and the second part of the waveform to try to check that the sort of parameters that you would recover, which is your sort of best fit data, from the first part and the second part according to general relativity match up. So that's one test of general relativity that we can do. Another one sort of looks at gravitational wave polarizations. And so what this means is when the gravitational wave hits the detector, in general relativity, it produces sort of two characteristic patterns of effects. However, in other theories of gravity, you can have additional effects for how the sort of detector responds to the gravitational wave. And so there are searches that people do to try to check that. There are some analyses, so we don't have sort of full waveforms in other theories, but a lot of the analysis goes into really checking that general relativity is consistent with what you see. So while you can't ask, is this weird theory motivated by string theory possible, you can really ask, how well do I know that GR matches this theory? And so for the detection, using some of these methods, they were able to sort of place like a 96% confidence, and then they're sort of limited by how accurately they can extract the signal. So there are certainly ways underway for LIGO. I know less about LISA, but I think you can sort of try to do something similar.
Yeah, this one would be, I guess, for Cameron. Astrid was talking about how you guys basically build a library of simulations, and when you take the data from the LIGO observations and try to match it up. Wouldn't it be possible to do just the opposite? In other words, just take the data from the observation, just use those as parameters that you feed into the computer simulations, and then you might get a more accurate representation of what's going on. Is that possible?
So just to repeat the question, as I understand it, when Astrid was talking about matching gravitational wave data, this is the gravitational wave data that you're specifically talking about. Okay. Matching the gravitational wave signal that's coming from the LIGO detectors and trying to fit that to the different waveforms that are coming out of the library of simulations, also like what Masha was just talking about as well. Wouldn't it be, your question is, wouldn't it be easier to go the reverse way, to take the signal out of the observational data from LIGO and then create a simulation that matches that? And it's actually quite challenging to do that. The simulations, essentially what they do is set up a number of different simulations of different parameters of black holes merging and different masses for each black hole, different ways that they're being flung into each other and going into the merger, and different timescales over which they're merging. And each of those scenarios is going to produce some observational signal, which we're calling a waveform, which then gets matched against the observational data. But the observational data, there's so much noise in it that it would have been, I mean, I guess the initial detection, it wouldn't have been as bad, but there's so much noise in the data that it's very difficult to discern what's the actual signal and what's just noise that happens to be there. It's kind of like if you stare at a television screen that's on a bad channel or that's detuned, and you're just seeing all the fuzz, the like popcorn there. It's just like shh. And if you stare at that long enough and you don't know what you're looking for, it becomes difficult to pull any kind of signal out of that. So for instance, like if you know I'm supposed to see, I'm tuning to this channel and I'm playing, with the bunny ear antennae from 30 years ago or 40 years ago. I'm dating myself now here, but you're playing with this and you know that you're trying to see a picture of a newscast where there's going to be a person standing behind a podium and giving a question. You know what to look for out of that signal, but doing the reverse, if you just stare at that and try and see something that's discernible, it can be, I'm not doing a very good job explaining this, but it's very difficult to do what you're asking, which is to do the reverse, to look for a signal and then program that into your simulations. Unfortunately, that would be much easier, but it's just not really possible. You think that's, do you want to add to that?
Yeah, so sort of to add to it's not really possible, usually when people try to do, so this is called like parameter estimation, so trying to take the data and sort of seeing what's the best match, they have to generate like millions of these waveforms to try to match it. Because the space of parameters is quite big, so you have essentially sort of two masses for the black holes, and you also have sort of their spins, so kind of how they're oriented, the axes on which they're spinning, so that's 6 more parameters, and those are just sort of the parameters that have to do with the binary locally. And then you get more parameters which have to do with, okay, how far away is it? Where is it on the sky? How is it sort of tilted relative to us? And so the overall parameter space is 15 sort of parameters. And so you really have to pick combinations of these, which will match the data. And so you end up, having to generate sort of millions of waveforms to try to compare.
These simulations, you use a supercomputer for those, or can I do it on my Commodore 64?
So these simulations, they typically run on 48 cores. And so a typical like MacBook, for example, will have 2 cores or 4 cores. And they'll run for maybe a month. So it takes a while to produce these simulations. And we only have, maybe like 1,000 simulations. So what a lot of people work on is trying to model the waveforms. So producing faster ways of generating these waveforms that look a lot like what the waveforms are. And then sort of they take the sort of numerical simulation waveforms, which are the sort of the most correct ones that we have, and then try to sort of tune their models so that they can match the simulation data well.
I don't want to address this too, but more of kind of a general question. Recently I read an article about the quantum entanglement experiment done by the Chinese scientists, where they shot the photon into the satellite and found that the properties are similar, kind of teleportation concept. So is there an analogous phenomenon where the gravitational waves are concerned, where the waves create at the same point and they're going in different directions? Would the same entanglement phenomena occur there as well?
That's an excellent question. So to repeat the question so everybody can hear, recently you may have read in the last week there was a news story about quantum entanglement between a photon that was on the Earth and essentially transmitting the information to a photon somewhere in our extended atmosphere. There was a spaceship or satellite overhead, and being able to transmit the information between those two places due to quantum entanglement. Is there an equivalent principle associated with gravitational waves where 2 gravitational waves emitted at the same time from the same location could have some sort of entanglement properties, and you could communicate that information from one to the other through this same principle? Does anyone on our panel know the answer? So it wouldn't necessarily. Well, so one of the big, so yeah, that's a good point, and this is related to that. One of the big goals of physics today is coming up with a grand unifying theory that combines all the forces that we have in the physical realm. The 4 main ones being gravity, the electromagnetic force, the weak nuclear force, and the strong nuclear force. And so far, we've been successful in combining 3 of them, all of them except for gravity, in a theory called quantum chromodynamics, QCD. But efforts like string theory and many of its derivations and such, or derivatives, are trying to combine gravity with these other forces, which are largely consistent with quantum mechanics, which is essentially what's at play with this entanglement discovery or whatnot that occurred last week. So right now, and I think this is consistent with what you were saying, Masha, gravity in terms of general relativity is generally a classical theory that doesn't necessarily have quantum components to it. So as we understand it right now, I don't think that you can have entanglement between gravitational waves. However, this is not my focus of research. It's not any of our focuses of research. And so I give you that caveat but I'm not sure that anyone could necessarily answer your question. I think that's fair to say. Do you guys think that's fair to say? Oh, okay.
So it should be emphasized that just like electromagnetic waves we know consist of photons, it's not crazy to suppose that gravitational waves consist of gravitons. So it does maybe kind of make sense to think about the concept of a pair of entangled gravitons, just like they had entangled photons in this experiment. But good luck measuring it, because if gravitons are a thing, we expect that they will be such a ridiculously hard thing to actually measure an individual one of that it would be an extremely ambitious experiment, to say in the least.
I don't remember it off the top of my head, but there is a number for how many gravitons were sort of released during the LIGO event. If anybody remembers it, we can. It's a huge sort of number.
So sorry not to have a super direct response, but yes.
Dark matter. Who's the expert on that?
Oh goodness, dark matter. Who wants to talk about dark matter? It depends on what the question is, I suppose.
Okay, so we've got all these optical telescopes, and we've got LIGO to measure gravitational waves, then we've got LISA coming out. So how are we going to find dark matter? What is the detector for that particular thing?
I can answer this unless somebody else wants to. Well, then perhaps you should.
No, you should.
Masha's worked on a dark matter detector, so I think she's the most appropriate to respond.
Are you sure? So maybe you can answer it on the sort of astro side, but on Earth there are, so it kind of depends on what you think dark matter is. And so there are a bunch of sort of proposed candidates for what it is, but one sort of proposal is that it's a sort of particle which sort of mainly interacts gravitationally because sort of we don't see dark matter, but you could expect it to sort of maybe interact weakly. And so there are some dark matter detectors which let's say they're sort of underground to try to shield from all sorts of noise and cosmic rays and stuff like that. And they usually have sort of a vat of noble gas, so like argon or xenon. And so what happens is if you have one of these sort of dark matter particles coming into the detector, so this is, for example, for something called like a WIMP, and they're a weakly interacting massive particle. So this is kind of what I have experience with. And so, this particle flies into the detector, it hits the sort of nucleus of this argon atom, and then that sort of releases, let me think, it's scintillator. So it releases, let's say, like an electron or something that hits a scintillator. You can detect light from it. So there are sort of lots of experiments like this, but so far none of them have reported a detection, except for one. But the detection that it reported had this sort of modulation on the period of a year, which kind of you can explain by dark matter, because sort of as the Earth goes around the sun, if you have an unequal distribution, you kind of hit more dark matter as you go around. But it might be due to sort of snow melting off of the mountain where it's located. So I wouldn't really trust the results from that. But sort of there are detectors that try to sort of detect dark matter on Earth, but so far none of them have come up with something. And then
Yeah, so she's done an excellent job describing this. There used to be alternative theories to what dark matter consisted of. So compared to the WIMPs, the weakly interacting massive particle, there were also the MACHOs, which were the massive compact halo object, which were consistent with there being small, massive, like black holes or planets or something like that that were massive and macroscopic sized as opposed to these microscopic sized structures in our galaxy, but they weren't necessarily emitting their own light. They were like planets. Planets don't usually emit their own light, so they were just these kind of dark structures in the outer parts of our galaxy. But there were a lot of studies looking specifically for these objects by gravitational lensing, where if you have a massive object in between you and me, light would kind of bend around it and lens. I would see you lensed and you would see me lensed because of its presence, and we didn't see a lot of structures like that, so it kind of ruled that out. But there is still the possibility that you could have macroscopic dark matter structures in our galaxy, but it's less likely. It's more consistent with probably what Masha was talking about in terms of these very small but massive microscopic particles that should be interacting. But yeah, so we've talked for 10 minutes and basically said we don't know what the answer is, but there are active studies going on by a number of different groups around the world to try and figure this out, because obviously this is a super important question to answer, that a significant part of the mass in our universe is some form that we don't actually understand. We understand how it behaves roughly, but we don't understand what it actually is. Yeah. Another question? No, you, sir. Yeah.
Can anyone on the panel update us on the Sagittarius A black hole situation? I've heard that maybe by the end of the year, we'll be actually able to see the shadow of the event horizon of the supermassive black hole. Does anyone know about that?
You guys want to talk about it?
Right, so the project he's referring to is called the Event Horizon Telescope, and the idea is that Sagittarius A star is the 4 million solar mass black hole at the center of our galaxy that the whole galaxy sort of orbits around. And the idea is that if we have a telescope with fine enough resolution, we can actually get a look at what this black hole actually looks like. So observations to date can see all sorts of fascinating stuff going on around the black hole, and in particular it flares up in the X-ray like every few hours, so there's a lot of interesting stuff going on. But so far nobody's actually been able to resolve the event horizon of the black hole itself, so the actual round shadow that you expect to see. However, as mentioned, this Event Horizon Telescope project basically takes a whole bunch of different radio telescopes and combines their signal together in such a way that we can get really high resolution. And yeah, apparently, from what I've heard at a conference, by the end of the year, I think was actually right, they're actually going to get a nice clear picture of the event horizon of Sagittarius A star. So it's very exciting.
So the news article that you were talking about, what they were reporting is that the observations were taken, but it's going to take a few years to actually ship the observations from telescopes all around the world to a supercomputer to correlate the data and get what could be turned into an image, and then you need to analyze that data and then turn it into an image, and this all takes a long time, so you can keep waiting for a little bit.
Do we know what future awaits our star, the sun? Is it going to turn into a black hole? What's this?
So the question is, what's going to happen to the sun? And there are in general, three fates a star can have. One is that it turns into a black hole, like we've been talking about all of tonight. The other, and this happens to the most massive stars, to an intermediate range of stellar masses, you end up with a neutron star. And stars that turn into black holes and neutron stars go bang. They're a supernova. Our sun is not that massive. Our sun will take a third path and become a white dwarf. So as the sun ages, it will puff up and eventually engulf the Earth and become very red and basically shed its outer layers. And what's left will be the core of the sun, which will be a little bit bigger than the Earth, but still very massive. So it's a very dense object. And this is what's called a white dwarf.
But don't worry, that will happen in roughly 5 billion years. So there's nothing, don't anyone freak out or anything. This is all a long way off before the Earth gets engulfed by the sun in this bad scenario. Oh, incidentally, I don't know if they've actually gotten the telescope trained on it, but you guys, I think, just came from out there. If you had the opportunity to look at the Ring Nebula, which I know is near zenith, directly overhead, the Ring Nebula is a planetary nebula, similar to what the sun will eventually form. So as Chris was saying, as the star ages, it sloughs off its outer layer, and you get this kind of glowing spherical cloud that surrounds the white dwarf, the core of the sun or the star. And so with this particular thing called the Ring Nebula, it appears like a ring because when you're looking at it, that outer cloud is still glowing, but it's around the edges where there's the highest density of material, so it appears like a ring, like a circle, and the white dwarf is right at the center. So I don't know if they have it in the telescope, but hopefully they do because it's pretty cool to look at.
Well, it's going to be a genuine question. What do you think about Stephen Hawking saying there's only 100 years left for Earth? What will you brought up here?
I think given global warming and there's only 100 years left for Earth, according to Stephen Hawking, and I think, well, I don't want to say out loud, but like given global warming and nuclear armament and stuff, I'm not very optimistic.
Ooh. I try to be optimistic. It's hard to be optimistic these days with the political climate the way it is and with climate change seeming to be accelerating. So I'll leave it at that. I don't want to get into the dirt of things, but it's not great. Do you guys want?
Like, okay, somebody says we've got 100 years to go before cataclysm, but like, the thing is nobody can really do that calculation right now because so many things can happen between now and 100 years from now. Things might get a lot worse. They might get a lot worse, but then somehow get better. Things might start improving sooner than we thought. But, you know, if somebody says they know what's going to happen in 100 years, you really have to take that with a grain of salt. And, you know, we're a very resourceful and resilient species, so I think we're probably going to be all right.
Do you think that was kind of a rallying call for everybody to start paying attention?
Everybody who's predicted Armageddon so far has been wrong, so.
I read recently that they're discovering a lot more brown dwarfs than they ever thought there were going to be. Is there any estimates like how much that has increased the
So the question is, with the increased detection of brown dwarfs in the universe, is it making up the difference of the dark matter? Or how does it affect? How far does it get us? Well, right now the ratio of dark matter, like the dark matter mass budget for the universe versus the baryonic content of the universe, which is us and all the protons and electrons and things in the universe, is what? It's 26% is dark matter, 3% is baryon. Is that right? Something like that. So a factor of 8 times more dark matter than baryonic matter. And yeah, say you find a lot more brown dwarfs, it's not going to bring you a factor of 8. I mean, not that that's what you were, yeah.
I was more just how much more is it increasing how much more baryonic mass do you think you have compared to what we originally thought with this?
That's a good question. I'm not entirely sure. I know that increasingly we're finding a lot more mass. So there are a couple of problems called the missing mass problems in the field, like the missing mass in our galaxy or in galaxies. And one of the places we're finding a lot more, okay, so the reason I say missing mass is we know the rotational rates of galaxies. And that predicts a certain mass. You have to have a certain amount of mass there by gravity to hold things and allow it to rotate at a certain rate. It turns out that a significant amount of that mass is actually in really hot gas that's in the outskirts, or in warmish gas that's in the outskirts. It's not hot enough to be emitting significant light of its own that we could see it with the instruments that we have, but it's not cold enough that would allow it to just kind of collapse and form stars. So this is a field that actually I work on called the circumgalactic medium, circum because it's around the galaxy, circumgalactic medium. But it's increasingly being shown to have, as much gas as there is and as much mass as there is in the actual disk of the galaxy, the part that we see when you look up and look at the, like the Milky Way or the disks of these systems. So that's one thing that I can speak to, and that's not really what you asked, but I'd say it's, brown dwarfs, the detection of brown dwarfs in the universe would be on the order or less of that total amount of mass that's in these galaxies. And
Is that circumvental mass? Or
the circumgalactic.
Did that increase to 3%? So you were thinking it went 1.5 and we discovered this now, now it's 3%?
No, it's more that we had only detected a fraction of the 3 or so percent that we knew was supposed to be around. Yeah. So it just helps getting up to the 3 or so percent that we know is there. Do you guys have other things you want to add to that? Go ahead.
Is there anyone that knows about the absolute speed of light? I pointed out the question before, but I couldn't get an answer. Like, when you have something that travels at the speed of light and you have a light source inside of that something?
Okay. What happens if you turn that light source on? Okay, so this is a common kind of paradoxical question. The question is, if you have something traveling at the speed of light that has a light source in it, so let's say you have a car. We'll say we have a car that's traveling at the speed of light and we turn on the lights, the headlights. How fast does the light travel coming out of the car's headlights? Well, you can't have a car going at the speed of light. That's the problem. The energy that it takes to build, to push things to go close to the speed of light, as you approach the speed of light, it takes more and more energy to get that thing going closer and closer to the speed of light. So let's say I've got this table and I'm pushing on it. Sorry, I don't want to mess up your writing. I'm pushing on it and it takes a little bit of energy to get it moving 1 mile an hour. And then it takes a little bit more energy to get it moving 2 miles an hour. Well, let's say I'm starting to, as I'm getting closer and closer to the speed of light, it's taking more and more energy. Not linearly so. It's taking more, I'm only going another mile an hour, but faster, but it's actually taking substantially more energy. And this is just a product of Einstein's special theory of relativity and general relativity. And that is to get actual baryonic matter, like we were talking about, like electrons and protons and things, up to the speed of light is nigh impossible. So the only thing that's zipping around at the speed of light is light, photons, light rays. So you couldn't actually have some sort of object that has a light source built into it, like a car or even a flashlight or something, actually get up to the speed of light in order to turn that on. That's
Okay, so what happens if you have two cars, one goes that way, the other one goes this way? They both go 100 miles an hour.
Yep.
So the difference is 200 miles an hour.
Right.
Okay, if you have same with the two light beams, is there?
Oh, you mean, okay, if you have two light beams that are traveling the opposite way past each other?
Yeah.
They still perceive the other, there's an absolute, so I know this is super counterintuitive because we have this intuition that two speeds will be additive to get the difference of the two speeds or whatnot, but that doesn't actually occur as you get up close to the speed of light.
Why not?
Because that's the way the universe functions. Why is it that when you drop an apple, why does it fall? Because of gravity. Like gravity is just our word that describes how the universe behaves in a particular way, and relativity describes the way the universe behaves in a particular way. I can't say why you can't just add speeds together.
Some form of resistance, but we can't define it in that term.
Why does it work with the cars and it doesn't work with the light?
Because it's called non-relativistic. It's low speeds. It works as an approximation at these very low speeds. It's actually not true that it's totally additive. It's just the small difference goes away in these very, very low speeds. And of course, 100 miles an hour doesn't seem like a low speed to you and me, but relative to this universal maximum speed of the speed of light, it's very, very small. I know because this paradox retains its mystique, that this isn't a very fulfilling answer for you, but relativity describes the way in which the universe actually functions for things that are traveling at very high speeds, and you can't add two speeds together to get the product of how they perceive each other as they pass each other in space. It just...
Where's this threshold? Like, where does this slow speed stop?
It never stops. It just diminishes to a very small kind of inconsequential amount. Even as I move like this, as if Masha were walking towards me and I were walking towards her, we would appear to walk past each other, and it would appear to be perfectly consistent that the speed at which I perceive her walking past me is just my speed plus her speed. But that's actually not true. There's a very slight relativistic effect. It's very, very, very small at these speeds, and we wouldn't notice it. But at very, very high speeds, you do notice it, and you have to take it into account.
I didn't know that.
So, sorry, I realize this is not like, you're not like, now I understand, because it doesn't make sense to us because we don't usually deal with things in this relativistic regime where things are traveling near the speed of light. We don't have an intuition for it because it's not part of our everyday experience. But that is, special relativity is amongst the most tested theories in the field of physics. People are always trying to come up with ways to test it and show that it's wrong, and it's always right. It's just that we don't have a really good intuition because we don't deal with relativistic effects very often. That's all.
What you said, that it's not double, it's actually a little bit less.
Yeah.
I mean, that explains it. So thank you.
Yeah. Do you want to add?
Yeah, and so to sort of give an appreciation for like what factor of the speed of light things are. So for the sort of LIGO event that we saw, when the black holes, and this was kind of like an extremely relativistic event, but when the black holes, let's say, sort of entered the LIGO band, so when LIGO started detecting these things, and as we saw, it sort of it lasted less than a second, they were moving at 0.03 times the speed of light. And then as they merged, they maximally got to half the speed of light. And then in terms of astrophysical objects that we know of like a pulsar, which is sort of the most relativistic pulsar we know, and that's at 10 to the negative 3 times the speed of light, to sort of allow you to sort of set a scale on what kind of things we can measure in terms of the speed of light.
Gentleman in the back.
Do we know if there was anything that happened or anything that existed before the Big Bang, or was the Big Bang itself kind of just a singular point driven from all space-time?
What's
So the question was whether we know if there could have been anything before the Big Bang. And you can't really rule that out, but we have a very particular theory about how the universe works. Like we can describe it in terms of general relativity. And when we talk about it in terms of general relativity, talking about a time before the Big Bang is like talking about a point on the Earth north of the North Pole. Like it's just not part of the system. It's now people can't really rule out like having different universes or something before the Big Bang, but if it were there, we wouldn't be able to see it, at least within our current theoretical understanding of how the universe works. But at the same time, the Big Bang is a singularity. In other words, it's somewhere where our understanding of how stuff works breaks down. So maybe if we were to gain some greater understanding about how the universe began, we would be able to start looking for stuff maybe beyond general relativity, which might hint at stuff before the Big Bang or outside the observable universe.
There are some scientists who are trying to make claims about what could have happened prior to the Big Bang. In fact, there's an esteemed mathematician named Roger Penrose in the UK who has published numerous books about this called Conformal Cosmology, and trying to look for signals in the cosmological microwave background, and now, in fact, in the LIGO signals, trying to say that there's evidence of certain information that we can pull out of prior to the Big Bang, but most people think he's wrong. Or at least most cosmologists and scientists think he's wrong. But if you want to read more about it, I would encourage you to look up Roger Penrose and conformal cosmology.
Oh, I just wanted to add, sort of for clarification, how did we sort of come to think of the Big Bang as a singularity in the first place? So if you look at things now, we know that the universe is expanding because we can see objects moving away from us, and sort of this is called like redshift and blue shift. And so since we know the universe is expanding, we can sort of think about general relativity and sort of think about how things evolve in terms of a set of equations. And if you evolve those equations not just forward in time, but backward in time, which you're allowed to do in general relativity, you essentially arrive at a singularity. So within the theory of general relativity, sort of the universe sort of started with a singularity.
Sorry, there was the next question. Yeah. The question is, during Astrid's talk, she alluded to the fact that you'd find fewer metals in older stars as opposed to more metals in younger stars, but why is that? And essentially, the main reason is that, as you alluded to, as a star evolves, it's turning light elements like hydrogen and helium into heavier elements like metals in its core, and eventually, either in a planetary nebula or a supernova, it ejects these, as it dies, it ejects these metals into the surrounding gas, therefore enhancing the metal content of the gas in that neighborhood. So future generations of stars then, forming out of that gas, they basically get all the metals that were enriched in that material when forming that star. And then it repeats over and over. So each generation has more metal in its, each subsequent generation has more metal in its star than the previous generation. So the oldest stars formed from the most metal poor material, but the youngest ones, it's gone through several different generations, so they have more metals that are there. Does that make more sense?
The more the recycling that has happened in the past, the more the chance of the newer stars have more.
Exactly. Exactly. And in fact, just as a short add-on to this, people are actively looking for the original generation of stars that doesn't have any metals in their atmospheres at all. And this is an active field of research looking for, astronomers have weird ways of describing these. There are population 1, population 2, and population 3 stars. So it sounds actually the reverse of what you'd think. Population 1 stars are the youngest ones, the ones that have lots of metals. Population 2 are older stars, and population 3 are the so-called first stars, the ones that wouldn't have any metals because they came from the primordial gas left over from just the Big Bang. And so people are actively looking for these kind of population 3 stars. Did you want to add to that, Mike? Okay. Any other questions?
So what are the heaviest elements that are present in stars that can be found?
So the question is, what are the heaviest elements that can be found in stars, right? Do you want to talk? Say it, Chris? Okay.
So generally when you think of metals in stars, we think of nuclear burning products. So first you fuse hydrogen into helium, and helium into carbon, and up and up and up. And this burning product metal stops at iron. So you might think that the heaviest element that we will see is iron, but we know of lots of elements that are heavier than iron, like uranium, that also exist. So they must come from another process. So they're not products of stars burning heavier and heavier elements. So there are two ways that we know how to do this, and one of them is called the S process, or slow process, and one of them is called the R process, or rapid nucleosynthesis process. And so the slow process works like you take an iron element and then you throw a neutron on it, and the neutron decays into a proton, and now you have iron plus 1. And you can keep doing this all the way up and up and up the periodic table. And the other way that you can make heavy elements is you take something like iron nucleus, you bombard it with 10 neutrons all at once, and then that creates an unstable nucleus, and they all decay, and now you have iron plus 10. And this rapid process, I think, is more interesting in that it's an active area of research where exactly in the universe this happens. I think the current leading theory is that you have two neutron stars colliding and throwing off their neutrons and bombarding heavy elements with lots of neutrons to capture and decay into heavy elements. And as to what the actual most massive element in stars is, I have a guess that it's uranium, but I don't know if anybody can confirm that. Okay, we think that's right. So if anybody else has anything to add.
Sorry. The heaviest naturally occurring elements, I think is uranium. I don't think there's like plutonium or thorium. Oh wait, no, plutonium or any of the higher ones. I don't think we ever have incidents of finding them. You have to produce them in a lab in some way. But yeah. Any other questions? We've got another 10, 15 minutes or so that you can hit us with whatever you've got. Do you have a question? No? You've got it all figured out? You should be up here.
I understand the after the Big Bang, the universe continues to expand, but it seems that it's accelerating, isn't it? It continually increases speed. So wouldn't that imply that there's additional energy that's being put in from some source to increase that speed? Where would that be coming from?
So the gentleman's question is, after the Big Bang, the universe is expanding, but we've recently discovered that it's actually accelerating in its expansion. What's causing this acceleration? Is there an additional energy source which is enabling it to accelerate in its expansion? Is that a good synopsis? So this is hard. This is an active field of research. Our understanding of the acceleration of the universe was only discovered about 1996, and maybe even a few years later. And it indicates the presence of what you may have read about dark energy, which again, we were talking about dark matter earlier and how we don't really understand dark matter, and we understand dark energy even less. One of the current leading interpretations of dark energy is that it essentially is a vacuum energy such that the more space between objects, the more acceleration is empowered to allow these things to accelerate. So it's kind of like an anti-gravity sort of thing. But does it rely on an energy source that it's somehow sapping from some things? I don't know. I don't have a really good answer for it. Presumably there's a field that it's drawing from, but I don't have a good answer for you. I'm sorry. I wish I did. But I don't think anyone has a super good answer for how it's all playing out, unfortunately. Leo, do you want to talk about this? No? Okay. Sometimes I call in a ringer from the audience here, who works on some of these things, but he's shaking his head. So. Anyone with an easier question? If someone can teleport, does it mean they can also time travel? Well, I guess it depends on what you mean by teleport. If you're teleporting, presumably by non-science fiction standards, by real physical standards, then you have to convey the signal from the entrance point of the teleportation to the exit point of the teleportation. And since the maximum speed at which we can transmit information is the speed of light, so I would, in this moment, transmit myself to the surface of the moon, even though the moon is, a light second away or something. Well, then I guess you just answered your own question. If you can do that, yes, then I guess you could time travel, but because you could just beam yourself to Jupiter or whatnot, even though Jupiter is light hours away from us. So that's a good question. I'd like to be able to teleport. I'm late to everything, so that would help a lot with these sorts of things.
It's different than slightly related question. So there's been theories that like the universe doesn't end, it actually wraps in on itself, and you can go in a straight line and come back to where you were. How does that deal with simultaneity? Because a lot of the intuitive models for dealing with simultaneity, you can say like, oh, if you're moving at a certain speed, then you can look at these things as if they're simultaneous, and you just keep going the other direction, and it makes events go simultaneous the other way. But if you're in a circular universe where it kind of wraps in a torus almost, then there's no good way to adjust that intuition, that like mental model of like, oh, events along this line are simultaneous if the line like wraps infinitely because it keeps going. I didn't word the question very well.
I'm having a hard time coming up with a synopsis of your question, like to repeat into the... If you're in a closed time loop, what do you perceive as being simultaneous?
Yeah, so sort of bringing us back to general relativity. So if we have, let's say, sort of two events, let's say something happens over here, something physical, like a physical event. Let's say like you have some, nucleus decays or something, or, I like tap on the table. And then you have an event that happens, let's say like hundreds of miles away, something else happens. So because of the nature of space-time, the most you can sort of say is how are these events kind of separated? And so what you measure between them isn't, just a sort of regular distance. Like I say, it's hundreds of miles away, but you have to account for the sort of time dimension as well. And so what you can do is you can measure what's known as a proper distance, which is sort of an invariant and sort of independent of your frame of reference. And so what you can say is, are these events space-like separated, which means that, even, let's say, you wouldn't be able to, essentially reach one event from the other, sort of no matter how fast we're going, or are they sort of time-like separated? So if you're sort of going fast enough, you can reach one event from the other, or they're sort of what we call null-separated, meaning that sort of light can sort of travel. So general relativity makes it hard to we're sort of very used to thinking about simultaneity, but in general relativity, that sort of goes out the window, and instead you have to think about like how things are separated in terms of this proper distance. But then if you sort of have the universe like wrapped around itself in like a torus or like a donut, let's say, how that would affect things, I'm not sure. Do you want to talk?
There's some fairly mathematical. This is Leo.
Hi, I'm Leo. There's some kind of very mathematically heavy stuff that's kind of esoteric for physicists, but mathematicians love this stuff, which says which kinds of spaces So what are their topologies? Like, are they just like like the ordinary three-dimensional space that we're used to, or like tori, like you were talking about, whether they can be tori in spatial directions or in time directions? Which of those can have a chronological order put on them so that it makes sense? So you can ask that question mathematically and say, if you consider that weird topological space as a physical space, is there even a consistent sense of time flowing forward in this space? And in some spaces the answer is yes, and in some spaces the answer is no. So in the spaces where the answer is no, the way that we usually think about the universe as, stuff happened at an earlier time and that determined what happens at a later time doesn't work in those universes. So at least in classical general relativity, we must not live in one of those universes. But that's kind of all that that's all I know about this topic. Yeah.
Thank you, Leo. Probably have time for one, maybe two questions. Yes?
Is there any more insight on, like concerning the double slit experiment, why the photons or electrons react differently when they're being observed or not? Is there any more insight on why?
Okay, the question is do we have any more insight, this quantum mechanics question, why in the double slit experiment where you send sets of either photons, light rays, or particles like electrons through two slits, why they behave differently if you're observing them versus if you're not observing them. So this is a classical quantum mechanics experiment demonstrating the particle wave duality of both matter as well as photons. I don't know. Who wants to talk about this? I don't want to talk about this. My answer is no. We don't have any more information about that. Well, I don't have any more information about that. Perhaps somebody else can. Yeah.
So I was told a few years ago in quantum mechanics that the very act of you can't observe something in a vacuum. Like by the very fact that you know something is there, you have changed it.
The first part of the sentence was you do not observe the vacuum.
Well, if you think about these photons, they're going to hit so you have the photon generator, you have the slits, and you have some screen that they bump into. And the thing you change in between experiments is whether or not you have like some camera where the slits are observing which one the photon goes through. But by placing a camera there, in order for the camera to know that there is a photon going through one slit or another, it has to interact with that photon. Otherwise, the photon will just, well, if the photon didn't interact with the camera wouldn't know the photon is there, and we wouldn't be observing it. Does that make sense?
Not quite. Because I wasn't really sure what they qualify as an observer. Is it the human eye? Is it the camera?
Something that could know the photon is there.
Because wouldn't the camera be able to just be recording?
But the way the camera records is a photon hits an electron in the camera, which sends, and that electron cascades into another electron, knocking many electrons down, and what the camera reads is those how many electrons did it did this like cascade see. And so if the photon passed through the camera but didn't hit anything, then it would just pass through the camera, and the camera wouldn't read any, wouldn't see any electrons in its detectors, and it wouldn't have known the photon was there.
I thought the camera was watching the outcome of the background. Or was it watching everything?
No, there's always a screen in the back because you have to, like, that's where you see the interference pattern or the ballistic pattern.
Yeah.
So what you change in the double slit experiment that makes it weird is that you place some other observer by the slit and watch which slit the photon or electron goes through. To draw.
So that, in addition to the back wall, and how the patterns are depending on the observer?
So you have let's do an electron. And then you have your screen. So, okay. So, in the double slit experiment, you have an electron, a slit, and and like some detector that sees where the electron ended up. So you have no knowledge of which slit it went through. So what you will end up creating is sometimes it'll go through this one, sometimes it'll go through that one. It'll go in like, you don't know which one it went through. So the electrons will interfere with each other.
And it passes through a vacuum, right?
It does pass through a vacuum. We can say it passes through a vacuum, yeah. So the interference pattern would look, what? I think I'm drawing this wrong, but yeah, okay. And that is what you'll observe because the electron will, in some sense, interfere with itself because there's a principle there's something in quantum mechanics called the de Broglie, I don't know how you say it. I don't think anybody does. Wavelength, where even if you have mass, if you're moving, there's a wavelength associated with that. So matter has wave-like properties. So it's not right to think of this as like a bullet. You can also think of it as like a wave, but that's another topic. That's electron interfering with itself. But if all of a sudden you put some detector here, and you can tell whether the electron is going from here to here, the very fact that you've put a detector there means that the electron will have to travel somewhere, maybe in this part, it's a wave, but then when you hit the detector, the electron has to interact with the detector in order to know where the electron is going. Correct?
The electron has to know, obviously, whether there's a detector.
Yes.
Yeah.
Yes, because
Right.
if it didn't, then you wouldn't detect anything because the detector didn't know anything about the electron. So how would the detector say, oh, I saw one electron, if